Pessoal, vamos finalizar o capítulo 6, ainda falando sobre embutimento, né, ou estampagem profunda, e precisamos falar de processos, digamos, melhorados da estampagem profunda, né? É aquela mesma visão que eu tenho trabalhado com vocês nas últimas semanas. Os engenheiros estão sempre em busca de melhorar os equipamentos, melhorar os projetos, melhorar as práticas, melhorar os processos, né? E pensando na melhoria da qualidade das peças embutidas, no aumento da versatilidade e numa deformação mais heterogênea em que a força é aplicada não somente de cima para baixo, mas em todas as direções, os engenheiros criaram o punção de borracha. Como que esse punção de borracha funciona, pessoal? Nós temos aqui, né, a matriz, a chapa, o punção e uma massa de borracha que, ao ser pressionada pelo punção, né, por uma força Fe, né, vai deformar a borracha e forçar a borracha a preencher o espaço entre a chapa metálica e a matriz. Este processo distribui melhor as forças e torna a deformação mais homogênea, né? Ou seja, a qualidade da peça conformada ela é superior a uma peça conformada puramente por puncionamento. E aqui você consegue trabalhar geometrias mais complexas, ok? Na busca de melhorar ainda mais, né, os processos de embutimento, os engenheiros pensaram: bom, existem limitações do punção de borracha, para cada situação você tem que ter uma massa de borracha específica, um SKU a mais, né? Mas assim a gente substituísse esse punção de borracha, essa massa de borracha, por um líquido. Então surgiu o processo de hidroformação, do inglês hydroforming. Você substitui a punção de borracha por fluido sob pressão. Então você utiliza apenas uma membrana de borracha, né, para garantir a vedação, né? E você tem o punção por baixo e formando a matriz, você teria o fluido sob pressão, né? Então você tem uma qualidade do processo ainda mais superior, o processo se torna ainda mais versátil. Vamos ver esse vídeo aqui. Né? É uma animação e depois a máquina real, né? É colocada a chapa, a máquina é selada, né? Porque estamos trabalhando com fluido sob pressão, altíssima pressão, né? Chegando a 10.000 psi, o punção atua e o fluido atua como uma matriz. Olha que fantástico, pessoal. Olha a complexidade dessa peça. Dificilmente a gente conseguiria obter uma peça assim por estampagem convencional. a peça pronta. Ok? E aí os engenheiros avançaram, né? Bom, e se a gente puder conformar, utilizando esta mesma metodologia, se a gente puder conformar tubos, dando formas complexas a tubos, utilizando no interior do tubo fluido a alta pressão. Fantástico, né? Então criaram o processo de hidroformação tubular, do inglês tubular hydroforming, né? Então você tem aqui as etapas, né? A matriz inferior superior, é inserido o tubo, é selado, é injetado fluido a alta pressão e a pressão que vai deformar, com o auxílio da matriz, deformar o tubo, né? Com formas das mais diversas. E vamos ver este excelente vídeo explicando o que acontece.
The Fundamental Manufacturing Processes video series, examining the tools and techniques of precision manufacturing. This program explores the fundamentals of hydroforming. The most commonly used method for shaping sheet metal components is by means of mating die halves applied to blank material. The die closing force is developed by a stamping press, and the tooling shapes the workpiece by direct contact with the sheet metal material. Hydroforming, in contrast, uses fluid pressure applied to a blank to form the desired component shape. Blanks used in the hydroforming process can be either tubular material or sheet metal material. Sheet and tubular hydroforming each have specific hydroforming process requirements. For this reason, operations are typically defined as either tubular hydroforming or sheet metal hydroforming. The most commonly used materials for hydroforming blanks include various grades of steel. These materials exhibit good fatigue properties, high energy absorption, acceptable corrosion resistance when coated, and excellent forming properties. Other materials used for hydroforming include stainless steels, aluminum, copper, and copper alloys. All hydroforming operations require hydroforming tooling and dies, a hydraulic press, and a fluid pressure intensification system. Sheet and tubular hydroforming tooling and dies vary dramatically. This tooling may be single cavity or multi-cavity to increase production rates. Hydraulic presses for hydroforming provide the die closing force against which the high fluid pressures are generated to form parts. The full force of the hydraulic press can be delivered at any point in the stroke, not just at the bottom of the stroke as with a mechanical press. The stroke of a hydraulic press also can be adjusted to provide optimal part clearance before cycling again. Moreover, hydraulic presses can be stopped in mid-stroke which is advantageous for some hydroforming applications. The fluid pressure intensification system mainly consists of a low-pressure, high-flow rate filling system and a high-pressure intensifier to raise the fluid to the required forming pressure. The forming fluid is water-based with additives such as lubricants, drying agents, rust preventatives, and bactericides. In a typical hydroforming operating cycle, a blank is placed on the lower tooling. Then the press is closed. Fluid pressure is then applied into the tubular section or onto one side of the sheet metal blank. The magnitude of pressure is high enough to cause the blank material to deform plastically, taking the shape of the tooling. Lubricants are especially important in hydroforming. Lubricants assist in reducing the friction stresses or forces at the tool blank interface, thus improving metal flow. There are several advantages to hydroformed components over conventionally manufactured parts. Conventionally produced multi-component parts can be hydroformed from a single blank, reducing part count and possibly weight. Most, if not all, forming and piercing operations can be performed within a single hydroforming setup. And scrap rates for hydroforming can be significantly lower than traditional stamping scrap rates. For these reasons, many major industries use hydroformed components, including the automotive, aerospace, appliance, and plumbing industries. Tubular hydroforming begins with the placement of straight tubes into the die, but is more commonly begun using preformed tubes. Preforming prepares the tube by shaping it generally into form for placement into the hydroforming die. Tube preforming can be done before hydroforming using either a rotary draw bending method and/or a preforming die. Preforming also can be done during the hydroforming operation, which is referred to as hydrobending. Sealing punches within the die close the ends of the tube, while the necessary fluid pressurization of the tube begins for hydroforming. This fluid pressurization typically removes wrinkles or imperfections in the tube. There are three surfaces at the end of a tube that can be used as a sealing surface. These are the outside diameter, inside diameter, and end surface. During forming, a combination of increased internal pressure and a simultaneous axial pressing on the tube ends by the sealing punches causes the material to flow into the contours of the die and the forming zones. Tubular hydroforming is generally divided into three classifications or operating techniques: low pressure hydroforming, or LPH, high pressure hydroforming, or HPH, and pressure sequence hydroforming, or PSH. Low pressure hydroforming is commonly defined as hydroforming at fluid pressures below 12,000 psi, or pounds per square inch, or 828 bar. Production cycle time for low pressure hydroforming is typically lower than that of high pressure hydroforming, but components must be carefully designed to form properly using the lower fluid pressures. With high pressure hydroforming, two blanks are placed in the die, and the die halves closed without pressurized fluid in the blank. Once closed, pressurized fluid is then injected into the blank, completely filling the material out to the shape of the die. In high-pressure hydroforming, fluid pressure commonly exceeds 20,000 psi, or 1,379 bar, and can reach 100,000 psi, or 6,895 bar. Actual pressure needed is dependent upon several factors, such as material yield strength, tube wall thickness, and the inside radius of the sharpest cross-sectional corner. When the tube is expanded by high pressure within the die cavity, material thickness may vary throughout the...
Observem aqui, pessoal, a grande vantagem da hidroformação, né? Você consegue fazer uma pressão em todas as direções e você então consegue deformação de detalhes em que você não conseguiria com a estampagem convencional, né? Observem aqui, né, que a pressão vai em todas as direções e você consegue preencher todos os detalhes da matriz.
Additionally, larger presses are needed for high-pressure hydroforming, and the higher operating pressures can result in longer cycle times. In pressure sequence hydroforming, the closing action of the press assists in the hydroforming of the blank. The blank is first placed in the die cavity, and the die is partially closed, partly deforming the tube. Low pressurized fluid is then pumped into the blank, allowing it to resist compression. At this point, the blank is much like a formable solid. The die starts to close again with the desired low pressure maintained while part cross-section reduces. Low internal pressure during die closure discourages pinching between the die halves. This liquid pressure also resists unwanted inward deformation. Once the die is fully closed, high pressure is applied to the fluid, forcing material into the corner recesses of the die cavity. When properly designed and managed, complex shapes can be generated from tubes with less pressure than needed for other hydroforming techniques. Maximum pressure is typically under 10,000 psi, or 690 bar. Also, with pressure sequence hydroforming, the tube is forced into the desired location and shape with no wall thinning, as the cavity and blank are of the same periphery and leave no room to expand. High-pressure hydroforming and pressure sequence hydroforming both affect the forming mechanisms of materials differently. For this reason, selection of the right material is fundamental to successful production. Hydroforming also allows for many secondary operations to be performed within the process. The most dimensionally stable, robust, and economical way to generate holes or slots in tubular hydroformed parts is to punch them in the hydroforming die during the forming cycle. This is referred to as hydro-piercing. Hydro-piercing tooling is built into the hydroforming die and uses a hydraulic cylinder to activate the punch. Hydro-piercings are typically pierced inwardly, with the punch creating the opening against the pressurized fluid. Hydro-piercings also may be generated outwardly using a plunger or backup punch, which retracts once maximum fluid pressure is reached within the part. The fluid pressure causes the surface material to fail, generating the hole. Generally, holes and slots can be positioned anywhere on the surface of a hydroformed part. The main limitation is the space needed to accommodate the hydro-piercing units on the tool and still maintain structural integrity of the tool.
Pessoal, eu vou parar aqui. O link do vídeo encontra-se lá no Moodle, tá? Para a gente economizar um pouquinho de tempo aqui da nossa aula. Além disso, existe o processo Cronenberg, né? Em que você tem fluido dos dois lados da chapa, né? do lado que seria o lado de punção e do lado que seria o lado da matriz, e você gradativamente vai aumentando a pressão de um lado e reduzindo a pressão de outro. A grande vantagem do Cronenberg é que ele deixa o processo ainda mais estável, né? Porque você retira a pressão de um lado e aumenta a pressão de outro. Então a deformação ela se torna ainda mais homogênea e de qualidade ainda mais superior. E aqui nesse slide a comparação entre o processo de hidroformação com punção e o processo Cronenberg, tá? Sendo o Cronenberg processo mais caro, porém um processo que entrega uma chapa deformada com maior qualidade, né? Então vamos falar um pouquinho sobre materiais para estampos. São utilizados aço, cromo e tungstênio com altos teores de carbono e cromo. Aços ao manganês, cromo e vanádio com altos teores de carbono e manganês. E aço com cromo, molibdênio e vanádio com altos teores de carbono e cromo, né? Velocidades para aço inoxidável, 200 milímetros por segundo, aço doce que tem uma maior conformabilidade, 280 milímetros por segundo, e alumínio e suas ligas, né, os materiais industriais mais utilizados em vários processos. Aqui é um pouquinho menos utilizado, mas ele tem essa grande vantagem de se poder conformar com as maiores velocidades ali na faixa de 500 milímetros por segundo. E aqui fotografias do processo em que você utiliza, né, a própria tira metálica como mecanismo de transporte até que a peça, após a última conformação, ela é cortada da tira, né, através de um funcionamento. Outro exemplo clássico de embutimento, estampagem profunda, é a fabricação de componentes para um automóvel, né? Vamos ver como é que é fabricada uma porta.
Car doors have come a long way over the last century. They're lighter for improved fuel efficiency and stronger to better withstand the force of an impact. They also now contain a lot of electronic gadgetry like speakers and power windows, all of which enhances the daily commute. A car door is one of the first things many people reach for as they start their day. So let's unlock the mystery of how it's made. It all starts with carbon steel, an alloy that's strong yet malleable. Machinery uncoils and straightens it. A large blade slices it to the desired length, producing sheets called blanks. Then it's over to a powerful press. This particular one is a trial press, which offers a better view of the process than the one on the production line. The press forces the blank into a die, giving it the basic shape of 2 car doors. It's a design that's been engineered for both aerodynamics and strength. Back on the production line, the main press is churning out car doors. An automated device with fingers then grips the newly shaped steel and transfers it to a punch cutter. It separates the 2 doors and trims the excess metal from the edges. With the outer door panels now complete, a handler inspects them for bumps, dents, or scratches. He approves only those that are absolutely flawless. The next worker arranges the window frame, a reinforcing plate for the hinge and the inner door panel, all in a special clamping fixture. Its fingers grip the parts to hold them in position as the fixture rotates and 2 robots move in to weld them together. At the next station, the worker arranges steel bars and tubes on a robotic platform. They add strength to the door, so it will better withstand any impact. He places the inner door panel over the bars and tubes. The robotic platform angles the parts for welding. Another robot applies adhesive to the rim of the outer door panel. More robots dab adhesive at strategic locations. the outer one. A special press then folds the lip of the outer panel over the inner one. This hemming gives the assembled car door a neater edge. With the inner and outer panels now joined, the car door undergoes rust-proofing, paint, and other protective treatments. Now, over on the assembly line, a worker fits the handle into its niche and bolts it to the door from the other side. Chrome trim is clipped into place. Moving down the line, a worker installs a small fixed window in the groove of the frame. He uses a plastic protector to prevent scratches as he slides the larger window into its slot in the door and links it to a powerlifting mechanism inside. He separates the two windows with a metal divider. At the next station, this car door gets an automated side view mirror. They're now ready for the inner panel and its workings. The employee wires the panel to the door and snaps it into place. He tests the power windows and they close to a tight seal, indicating a successful installation. A special elevator now lowers the completed car doors 6 meters to the next station. A worker unloads each door with the help of a pneumatic arm. This device shoulders the weight of the part and correctly positions the door for installation. He drives bolts into hinges to attach the door to the car. On the door side, the heavy-duty reinforcement plate surrounds the hinges and supports them. The whole weight of the door will hang on this plate as it swings open and shut. With all the panels installed, it's time for the final adjustments. They call this finessing. They examine each panel to confirm that it's flush to the rest of the car body, and they tweak the installation job where needed. Finally, they're satisfied the assembly is airtight, so it's time to close the door on this production.
Está aí. E outro produto, né, que o processo de estampagem é clássico, né, na sua produção, é a famosa latinha de refrigerante, né? São duas partes diferentes, né? A tampa, né? Aqui começa aqui, vem para cá, vem para cá, vem para cá, vem para cá, vem para cá. São três partes diferentes, né? A tampa, né? O lacrezinho, né? Que é de baixo para cima, tá? O processo. Daqui, daqui e daqui. E o mais importante, né? O corpo da latinha. Começa com um disquinho de alumínio, vira um mini copinho, operação de corte, embutimento ou estampagem profunda, e as próximas operações de estiramento com detalhes ali, né, de conformação no fundo da latinha. Vamos ver como é o processo?
The next time you buy a canned soft drink, consider this. That aluminum can will always be recyclable. Unlike plastic, aluminum never deteriorates, no matter how often it's melted down and used again. Aluminum cans are so lightweight that it's hard to believe they're made from a huge roll of aluminum sheeting that weighs almost 10 tons. The sheet is about 5 feet wide and as thin as construction paper. A roll like this is long enough to make 750,000 drink cans. The sheet feeds into a press that punches out round pieces that'll be formed into cans. The punch press actually performs two operations. It punches at a disc 5.5 inches in diameter, then bends it into a cup. What's left of the sheet gets compacted and sent back to the aluminum factory, where it's recycled into new rolls. The cup goes into a machine called the draw and iron body maker. A A tool draws out the aluminum, forming the body of the can. The tool is lubricated so it won't tear the aluminum while stretching it. The lubricant also acts as a coolant because the aluminum heats up as it's being worked. Once the body is formed, a trimmer cleans and straightens the edge. Now the cans move along upside down on the conveyor belt, over to the washer. The washer performs a 6-stage cleaning. The first 2 washes are in hydrofluoric acid at 140 degrees. The last 4 washes are in deionized water, neutral water with no pH, also at 140 degrees. The cans come out of the washer and go under a hot air dryer. They're now shiny because the hydrofluoric acid wash removed a thin surface layer of aluminum. Next, a roller passes over the cans, coating the bottom rims with varnish. This varnish coating allows the cans to slide easily on the conveyor belts and in the vending machines. It shows up as a blue ring under an ultraviolet light. The cans are now ready to be printed. This rotation printing system can apply up to 5 colors, one at a time. The machine then applies a layer of varnish to protect the ink. This is what the print and varnish process looks like in slow motion. And here's the actual speed, 1,800 cans per minute. Next, the cans fly through an oven that instantly hardens the ink and dries the protective varnish. The next machine sprays a water-based varnish on the inside of the cans. This creates a barrier between the drink and the aluminum, so the drink won't end up tasting like metal. It also prevents the aluminum from being eaten away from the inside by the acid in carbonated drinks. Next, the cans go through a machine called the necker, which forms a 2-inch neck on the can. This is done gradually in 11 steps, so as not to puncture the paper-thin aluminum. The next machine, called the flanger, forms a curved-over edge at the top of the can, which will later attach to the pull tab cover. The cans pass through a sophisticated vision system that photographs the inside of each can. Any can that doesn't meet standards, that has a bump or ink inside, for example, is automatically removed from the production line. They strap the finished cans onto a pallet. From here, they're shipped to the drink company, which fills them and then attaches the pull tab cover.
Ok. Esta é a lista de exercícios. Eu recomendo, né, que apesar do tempo escasso, que vocês respondam, né, para se prepararem para a prova de terça-feira. Tá bom, pessoal?